Need the microphone on. Probably required it.
Well, happy Halloween, and great to see everyone. I guess you guys all have capstone as a scientist, right? Assume. And great, and it's my pleasure to introduce Carl Agee, and I'm looking forward to the talk. And Carl and I go way back in New York City, and he was at Columbia. I was at City University about the same time, and we actually had a mineral physics clubs and met once in a while and in restaurants or museums, and I think all of us graduate students was benefit a lot in the great New York area. So, since Carl has been moving on and made many scientific contributions, and also he moved from Harvard to NASA and JPL, JSC, yeah. And then now he's the director for Institute of Meteorite and at New Mexico. And he has broad interest in experimental charges and experimental charge, and as well as planet science. And his latest passions are meteorite. And at one point, you had a job title as in charge of all the lunar samples. I think that's pretty cool. And when you talk to your in-law, says what you do, I'm in charge of all the lunar ones. But now he's much more in charge of all the meteorite. So he's the man if you need a piece of rock from outer space.
So I can start?
Yeah.
Okay. Thank you for that that great introduction. And today I'm going to talk about Northwest Africa 7034, also known as Black Beauty, unique water-rich meteorite from ancient Mars. And here we have a photograph of Black Beauty and two of its parents that were found in the Western Sahara in 2011. And but before I get into the story of Black Beauty, it's a really interesting story. It's something that's really pulled me in. I just wanted to give a few plugs for what I'm doing currently. And Faye referred to the Institute of Meteoritics. Well, we have a brand new renovated meteorite museum. So next time you're in Albuquerque, make sure that you drop by the Meteorite Museum. This museum has actually been in existence for, the Institute has been in existence since the 1940s. And our museum was established as a public space in the early 70s, and it hadn't been renovated for all that time. And finally I got it renovated. And so it's a spectacular space. So anyway, come and take a look at that. Aside from a great display, we have about 1,000 different meteorites. Many of them are, of course, great objects for research and study. The other thing that I'm doing right now, and it's coming up on my one-year anniversary as president of Compress. And Compress, many of you are familiar with Compress. Compress stands for the Consortium for Materials, Properties, Research, and Earth Sciences. And this is a photo of our annual meeting that was held just north of Albuquerque at the Tamaya Resort down on the Rio Grande. So you're seeing the Rio Grande cottonwoods in the foreground and the Sandia Mountains in the background. This is was a wonderful setting for our annual meeting. And I'm really excited about leading Compress now. This is this community-based consortium that promotes earth science research. And we have a presence at some of the important beamlines nationwide. This is a National Science Foundation cooperative agreement. It's funded through GEO and EIR, specifically the instrumentation and facilities part of that. And I'm the PI of it, but we also have sub-awards. And you'll see that actually Carnegie is a sub-award partner in this activity. And so in any case, I want to, enough of my, about what I've been up to, I'd like to now go ahead and tell you the story of Black Beauty. So this is a photograph of the meteorite a short time after I started to delve into it. And what I mean by that is, well, first of all, I received this sample back in the fall of 2011 from an American meteorite collector who had purchased it from a Moroccan meteorite dealer. And it arrived in a box by UPS or by FedEx or something, and I opened it up and I took a look at it, and I've been in contact with the collector, and he said, "Carl, you know, what is this? You know, is it even a meteorite?" And when I looked at it, I realized I'd never seen anything like it. You know, I see meteorites all the time, and they're all over the place in my office and in my lab and so forth. So I'm pretty familiar with what most meteorites look like. This looked a little different from anything I'd seen. And because of that, I actually shelved it. I literally put it on a shelf, and it sat there for a couple of months. And then finally one day when I didn't have anything better to do, I said, well, you know what, I'm going to put this on the diamond saw and cut it open. And so I cut it open, and lo and behold, there's this dazzling breccia that was revealed from that first saw cut. And it was a breccia, again, like no breccia I had ever seen. It didn't look like a lunar breccia. It didn't look like any other type of meteorite breccia. And so I proceeded to study this. And the first thing, of course, that you do with meteorite samples is you make a thin section or a probe mount, and you take it in and start analyzing it. The first thing that I always do when I'm looking at a new meteorite that's unknown, that I'm not quite sure where it's from, what sort it is, I analyze the pyroxenes, and if there are pyroxenes present, of course, and there usually are. And I pay special attention to manganese and iron. So this is a plot of iron versus manganese and atomic formula units. This is a diagram after Popike. And Popike showed that this iron-manganese ratio can be used to distinguish between rocks from the moon, igneous rocks from the moon, igneous rocks from Mars, Earth, and also from the Agee parent body that produces the eucrites, the howardites, and the diogenites. This may be the asteroid 4 Vesta. So anyway, I analyzed 349 pyroxenes, and this is what the plot looked like. And so I'm thinking, this is interesting. They're all plotting on the Mars trend. That's the red line that you see there. They're way off the moon trend. They're not coinciding with the Earth trend. So this looks really interesting. It turns out that this is not a typical Martian meteorite. It is a Martian meteorite, but it took a lot of work to prove that it's a Martian meteorite, mainly because it's a new type and it's unique. And so approximately, gosh, it must have been, well, it was more than a year later, we finally ended up publishing a science paper on this meteorite. And you can see that some of the co-authors are actually in the room. Stephen Alardo. Marilyn is not with you guys anymore, but you all know Marilyn Vogel and a few others. Andy Steele is also a co-author on this. The point of it is that I reached out to a number of people who have labs that do work that were key in trying to establish that this meteorite was indeed from Mars. And in fact, for a long time, I would, well, maybe not wake up in the middle of the night, but I'd get this nagging feeling like maybe it isn't from Mars. Maybe it's. In the beginning, I thought it might even be a meteor rock. It might have been just some weird terrestrial rock. But now all of the evidence is in, and now I can feel confident in saying that this is a Martian meteorite. So let me tell you some things about this. First of all, let me. I think we skipped a slide there. Yeah, there we go. Let me just first of all tell you a few things about Martian meteorites. And most of you obviously know that Martian meteorites are these pieces of Mars that have been blasted off through impacts, and they've of course gone out into the solar system, and we're lucky to have some of them land on Earth, and we can collect them as meteorites. And this was established back in the 1980s, that this group of meteorites called the SNCs are actually from Mars. And there's a number of lines of evidence to support this, like trapped atmospheric gases, radiometric ages, showing that some of them are geologically speaking young volcanic rocks. And of course, and there were originally 12 Martian meteorites. Now, currently, there are over 150 in the world's collections that have been classified. And this number is growing all the time. And in fact, if you want to know how many there are, you can click on this link, and it'll take you to the Meteoritical Bulletin, and you can find out how many Martian meteorites that have been classified, and lunars and any other meteorite. There have also been 5 falls. These have been witnessed falls. The most recent one took place in Morocco in 2012. The rest of them are coming primarily from hot deserts, mostly from Northwest Africa, from the Sahara Desert. And currently there are many kilograms total of Martian meteorites. Now, this is just a little wiring diagram to show you what the situation was like with Martian meteorite classification classically. So there were these 3 groupings: the Shergottites, the Knocklites, and the Chassignites. And these were the Shergottites are basaltic to lertzolytic igneous rocks. The Knocklites are clinopyroxenites. And Chassigny was a singleton that is a dunite cumulate. And these formed this so-called SNC group. Then back in 1984, ALH, which stands for Allen Hills, 84001 was collected in Antarctica. And it took almost a decade before it was identified by Dr. Mittelfeld as a Martian meteorite, just a new type of Martian meteorite, not one of the SNCs. It's an orthoperoxenite-rich Martian meteorite. It was actually originally classified as a diogenite, and it took a while before that was sorted out. Now, in the meantime, what I'm talking about today is that we have another new type of Martian meteorite that doesn't fit into the SNC category. And this is now called the Martian basaltic breccia, BBR. And this is how it is described in the Meteoritical Bulletin. It's a Martian meteorite that is a breccia dominantly composed of basaltic class, and it's not assigned to these other groupings. And just as a side note, we found yet another one. I'm not going to talk about this one today. This is a whole other talk, but we found this new type of Martian basalt called an Agee basalt, and it is different yet again from the Shergottite, Knocklite, and Chassignyte groupings. It's also different from Black Beauty. It's different from the OPX. And it also, I think it shows us that the more meteorites that we look at, and the more that we get new Martian meteorites in, we start to see glimpses of the igneous rock diversity that actually exists on Mars. You know, Mars is a presumably recently active, geologically active planet, and it has. I'm sure that it has a rock sweep that goes way beyond the SNCs. In fact, we see that from the rover and the orbiter data from NASA missions. Okay. So let me tell you a little bit about where this meteorite was found. It was found in Western Sahara. Here's just a map of sort of the northwest coast of Africa for your reference. So here's Morocco, and here's Mauritania, and Mali, and Algeria. Here's Western Sahara. And this is what the field area looks like in the Western Sahara. So you can imagine, as a meteorite hunter, this is an awfully good place to look for meteorites. It's got the same sort of, similar sort of characteristics that are desirable in Antarctica, where you have a field of blue ice and any black rock sticks out like a sore thumb. Well, that's the same deal here in the Western Sahara. Just a little different climate. And this is actually a meteorite hunter. And he sent me this photograph. saying, this is where Black Beauty was found. I had no clue where it was from originally. You know, I just knew it was from someplace in Africa. And so I've been in contact with people who did the hunting. And this is actually a slide from Science magazine. They did a piece on this about a year after our science paper came out, just talking about the find and so forth. It turns out that there's actually a strewn field in western Sahara that is probably about something like 10 kilometers long where these pieces have been found. So that original piece that I had was 320 grams. There turns out to have been, there are more pieces that have been found in the meantime. And the reason why there were more found is because we established that it was a Martian meteorite. If we had established that it was an insignificant rock, no one would be looking for it. But now it's like looking for treasure out in the desert. So by 2012, 2013, hundreds of meteorite hunters were combing the sands of this field area for Black Beauty. They found pieces like this 241 gram specimen sitting here. And again, this is courtesy of Eric Hand from Science magazine. And this was the cover of Science, and I love the title, Object of Desire, a castaway from ancient Mars. So it's an object of desire. Obviously, you know, we all see this as an object of desire for research and science, right? Because it tells us about the planet Mars, it tells us about igneous petrology, it tells us about other things that I'll get into in a little bit. But it's also an object of desire for the collectors, meteorite collectors, like the individual who sent Black Beauty to me, because he has his own private meteorite collection and he's obsessed with meteorites. He's not a scientist, but he is obsessed with them as objects. And also the story that's bound up in them. And then it's also an object of desire because it has value. It has a monetary value. And so the hunters are out there finding these meteorites so that they can earn money. And then the dealers obviously want to make money on these as well. So there is this interesting triangle of people who all want to possess this. The scientists want to have it, the collectors want to have it, and the dealers want to have it, all for their own selfish reasons, right? Here's an example of some of the additional recovered stone. This is that one that you just saw in the picture that was in the sand. This is now is in my lab on my desktop. So I got a lot of these to look at and catalog, and we're still in the process of working through these. Most of the additional recovered pieces have not been studied. So we've I've cut into that original main mass, and then there are a couple of others that have been sawed open, but most of them remain untouched. And so there's actually probably going to be a lot more coming out of these. And the reason why that is because, as we'll see later on in the talk, these objects are very complex. It's not like, well, if you have just a hunk of basalt, right, one basalt is the same as the one right next to it, so it gets kind of boring after a while just looking at that same texture. But this has a variety of different textures and different parts to it. That means that in a way, every time you look at a new piece, you may see something different, something new. So this is another piece of Black Beauty. It's a different stone, not one of the ones in that picture and not the original one, but one that I came into my possession through a collector, and we have a piece of this in the museum. We have several pieces in the museum now. And I cut into it and polished this surface, and I'm just holding it, taking a picture of it with my phone camera. But what you can see here is that this is a very complex breccia. It's the first and only Martian breccia. And if you go into the Meteoritical Bulletin, you'll see that there are a number of these so-called NWA numbers. And it turns out that these are all the same meteorite. They're all from the same meteoroid. They're all Black Beauty. But the way that the Met Bull deals with them is every time somebody gets a piece of this and wants to classify it, it gets a new name, a new number, and that's the way they catalog them. They do the same thing for meteorites from Antarctica. Currently, there is about 2 kilograms of black beauty, but just like that other slide showed, that there are people hunting. There are people hunting right this minute. Well, I don't know. It's probably nighttime in Morocco right now, but every day there are many hunters out combing the area looking for it. And I just heard this fall they've already found 2 new smaller pieces of it. So they're still recovering samples. Now let me just talk a little bit about meteorite breccias. And again, in terms of Martian breccias, this is a breccia made up of many different types of clasts. So there's no Martian meteorite that's like this. There are some Martian meteorites that are broken up and sort of welded back together, and they're fragmental in that sense, but they're all more or less the same lithology. This resembles more the breccias that we see from the lunar highlands. So this is a lunar feldspathic breccia. This is a lunar meteorite, NWA 2995. And you can see large feldspathic clasts, and then there's a dark ground mass. It's made up of pyroxenes, olivines, and shock melt, and so forth. And then this is a breccia from the HED parent body, presumably the asteroid Vesta, and this is a howardite. That's this is NWA 6817, and so they're similar to Black Beauty, to 7034, but not exactly. For example, in Black Beauty, we have these very interesting spherical objects that are scattered throughout, and none of those other types of breccias have those. So we'll talk a little bit more about that later on. I just wanted to give you an idea of what's in this breccia, and it turns out that there are something like half a dozen igneous rock types that are present, and they're mostly sort of millimeter-sized fragments, and some of them look like like this one. These are backscatter electron images. Sorry about that. And so what we're looking at here is essentially different shades of gray, giving chemical information. And so this one here, this is actually a microgabbro of plagioclase and pyroxene, and then it has here some oxides like this is goethite and baryhydrite and pyrite and so on. So this is a little rocklet, and it's in a matrix, a fine-grained matrix. Here's another presumably igneous class. This one actually has K-spar, and apatite is abundant in this one, also plage and pyroxene. This is a very strange igneous class. This is one that doesn't have a terrestrial analog. It is rich in chlorine-rich apatite, ilmenite, plagioclase, and K-spar. It's a very unusual bulk composition. And then some of the igneous class end up being single crystal fragments that are presumably from a larger, coarser-grained igneous rock that has been disaggregated, and we see only fragments of that let's say that gabbro. And so these are scattered throughout the meteorite. And so we have igneous rocks, clear-cut igneous rocks present. But we also have a bunch of secondary alteration objects present. In addition to what you saw, maybe you can see it here, there's this fine-grained matrix. This is 100 microns here. So many sort of micron scale fine-grained materials that are sort of the background for everything. And then we have these clasts that are rich in iron oxides. A lot of this is magnetite or maghemite, but some of them are feldspathic or pyroxene rich, like this one. We call this one affectionately the paramecium. So, not to say that we found life on Mars, but we found something that looks like a large paramecium. Maybe paramecia on Mars are big, this scale. Who knows? But anyway. It's not that that's a unique one. I mean, there's this one thin section where these things there are like a dozen of those that are sort of in this little, they're swimming in a stream. I don't know. But it's very strange. But so the point of it is we've characterized those igneous clasts really well because a lot of us are by training igneous petrologists, and We understand hard rocks. When it starts getting into these alteration products, that's when things start to get very hard to interpret and hard to characterize. But we're still working on that. Just a note about the spherules. They're all over the place. They're in different scales. They are from micron to centimeter scale. This is just a photograph of a slice out of the original main mass. And I've taken the liberty of highlighting the spheres sitting in here. And of course, spheres are something that are very common on Mars. And we're seeing this in Black Beauty. You see it at Meridiani Planum, of course, the blueberries, but also at the Gale crater site, there are a number of lithologies that have spherules as well.
What's the scale on that?
On this one, not sure. I think the blueberries are like millimeter size, so multiple millimeter size. Bigger than the ones in Black Beauty. But you know, the trouble is we're working with a hand sample. You know, we'd love to have like a boulder of this, you know, so we could get go up a scale in that. But that's sometimes a limitation with meteorites. Let me just summarize the mineralogy of 7034. This is not your average igneous rock. It has 18 minerals so far as identified that are present. Some obviously more abundant than others. The most abundant ones are at the top of the list. Plagioclase feldspar, but also alkali feldspar, going all the way from K-spar to albite. We have 3 pyroxenes. Magnetite is very abundant in this meteorite. I would say it's probably at least 5, maybe more % magnetite. But there's also an iron 3+ plus water version of that, sort of a maghemite, so not hematite, but maghemite. Ilmenite, berihydrite, clay minerals, primarily phyllosilicates, chlorine-rich apatite, chromite, pyrite, marylite, rutile, zircon, bedelite, and even a stray olivine once in a while. But olivine is a trace mineral in this meteorite. Turns out that this meteorite is high in water content relative to other Martian meteorites. Sort of water-like in the sense that it has a lot of the minerals that we see in Earth rocks that are on the surface of the Earth, you know. And so it has maghemite that bears water, berihydrite, obviously the clays, and chlorine-rich apatite. And by the way, this photo here is another image of a thin section, and this is 6 millimeters for scale. You can see one of the prominent spheres here. This is if I go back, you can. So red is iron. This is a false color chemical map. Red is iron rich. Blue is aluminum rich. So those would be the feldspars, and then green is Mg. The other interesting thing that NWA 7034 has, and it also allows us to get a handle on age dating, is that it contains, as I said, chlorine-rich apatite, but also zircon and bedelite. And I have a couple of slides later on that highlights this, so we'll get to that in a minute. This is a classic volcanic rock diagram. SiO2 plotted versus sodium and potassium, showing, you know, basaltic andesite, and so on. It's used a lot to describe Martian rocks, Martian igneous rocks. It's used by Hap McSween and others. And it shows down here, for example, this purple field are the SNC basalts, the shergottites, the knocklites, and the chastognites. Actually, they're really the shergottites that plot down in here. And this pink rectangle is the field for the Mars exploration rocks and soil at Gusev crater. And you can see that and one of the interesting things about that, about a lot of the studies that NASA has done remotely on the composition of the surface of Mars, is that it's a poor match for the SNC meteorites. It's it's an enigma. It turns out that Black Beauty, in its bulk composition, even though it's made up of a bunch of different lithologies, its bulk composition overlaps with the surface of Mars, as seen by the Mars rovers. Here is Adirondack. That's a basalt from Gusev. And then the MSL is actually finding some very interesting rocks that sit higher up in terms of potassium and sodium. The point of it is that Black Beauty is more like the Martian surface in terms of its bulk composition than any other Martian meteorite. However, as I said, it's made up of different lithologies. So Alison Santos, my PhD student, has identified all of these different compositions. These are all different igneous rock compositions in Black Beauty. Now some of them overlap, so some of them are probably the same type. But you can see they span all the way up into basaltic trachyandesite, down into more silica-pore compositions. And she's even found some compositions that plot off of this diagram that are very low in silica. The other thing that we had done along the way, in collaboration with Cartwright, was to determine whether or not there was Martian atmosphere present in the form of noble gases in the meteorite. This is one of the things that people are always pointing to as proof that these meteorites come from Mars. It's one of the original things that, say, Don Bogart did with some of the Shergottites to nail down the hypothesis that that SNCs are from Mars. And it turns out that the argon in Black Beauty is very similar, actually, to the curiosity values. This is the Viking values up here. So we've in addition to all of the other studies that we've done, we've also established, because of Julia's work at Max Planck Institute, shown that there are Martian noble gases or Martian atmosphere trapped in the meteorite. The oxygen isotopes were very peculiar in the beginning, very hard to explain, and in fact, early on, after we'd done a lot of microprobe work, I had gone to Zach Sharp and I said, Zach, could you do the oxygen on the sample? I think it's from Mars. And he came back and he said, good news, Carl, it's a meteorite. Great, okay. He said, sorry, it's not from Mars. And I said, what do you mean? And he said, well, it plots, I think the first analysis he did plotted up here somewhere. And so in the meantime, you can see we did a few more analyses. I said to Zach, could you do another analysis? He said, why? And I said, well, because, I'd like to confirm that this is not some anomalous measurement. He goes, oh, the measurement's perfect, you don't need another data point. So, but we went ahead and did it anyway. And we also sent some sample to Mark Thiemens at UCSD, and he did a few as well. I got somewhat obsessive about this. And so, much to the chagrin of Zach. So, but anyway, it turns out that this is offset from the main SNC grouping. Although we do have a few, and I think what we're sampling some of the heterogeneity in the meteorite, sampling some that actually plot down here in the SNC field. But the way that we interpret this is that there is a component that sits out here that this rock has been interacting with in the Martian atmosphere and hydrosphere that has a higher 1817 value, and this is in accord with a lot of with some studies that have been done on Martian alteration products. Ittingite, for example, in I believe it's Knocklights, plots way up in here somewhere. So that's the explanation for the anomalous oxygen isotopes. The other thing that we, of course, did was to do age dating, and the first cut at this was a rubidium strontium study done in Yamani Asmaram's lab at UNM. And it came back with a roughly 2 billion year old age, 2.1. And this this is actually an incredibly tight isochron. This is a blow up of this area down in here. And of course we have this light component. These are all handpicked. So Imani was very excited about this, and he really liked the looks of this data. He also had done some samarium neodymium work, and it was a mixed bag. And now in retrospect, looking back on it, it's not surprising because it's a breccia, right? It's not a single lithology. So there's probably a lot of complexity that's in here. And so the question about this age remained well, we need to do more work. And so we sent some sample to Larry Nyquist at JSC, and Larry said, this is one of the last meteorites I'm going to analyze. He said, I'm retiring, but this is so interesting, I'm going to work on this. So we got Larry to do that, and he came back with a samarium neodymium age of 4.44 billion. And so clearly there's something interesting going on here. I told you that that there are zircons and bedelliotes in this meteorite, and this is absolutely such good luck, because this allows us to go in and look at individual domains within the meteorite and get pinpoint dates on them. And the funny thing about it is, I worked on this rock for several months. We had this on the probe, and we were working on it, and then one day I was, I don't know where I was, and I was talking to Munir Humayun, and he says, it's full of zircons, right? I go, what? And he goes, yeah, there's zircons all over the place in this. And I was like, okay, let's go look. So they're literally everywhere. And so that's the slide. This is a slide here, of course, regular microprobe slide, inch across. This is my hand for scale. And this is the backscatter image of that. This is the early work that we did. Francis McCubbin did a lot of this. And what you see in here are zircons that are circled in green with an age. So there are some zircons that are 1.4 billion, but there are also some that are 4.4. So these two bedelliotes are 4.4. So what they got out of the zircon data and the bedelliite data was an age that was in agreement with the samarium neodymium, but there's another age that's in there. There are younger zircons and there are older zircons, basically. Now, in the meantime, Francis has done a lot more work on this. Francis and colleagues. This is a paper that's going to be coming out in JGR Planets soon. A cast of thousands. I'm the last author on the Steve, just like you were on the science paper. But I'm on it because I didn't do any work, So. But anyway, the neat thing about this is that he's found many more zircons just in this one thin section. And in fact, you can see the different lithologies just on the distribution of zircons. So there's actually in here what he calls a protobreccia clast. It has a slightly different ground mass than this ground mass out here. And you can see indeed that there are many more zircons, which are these blues, and then a few scattered bedelliotes. They refined the young age to be about 1.5 billion. The old age is still 4.4 on this one. And by the way, in this picture down here, this is a potassium K X-ray intensity map. You can see this is a really just an example of how chemically mixed up this meteorite. These are this is all full of K feldspar. This class here and here. So everywhere where you see a little orange streak or orange speck, that's a K spar in the middle of a basaltic breccia. So Francis and co-authors have come up with they're trying to work out the geologic history on this and try to understand what that young age means. And they think it's possibly two things. It could either something happened that thermally reset the meteorite that mildly annealed some of that fine-grained matrix. So they're attributing it to either some sort of pyroclastic volcanism or an impact. And there are people who they see all the craters on Mars and they say it's probably an impact event, but we can't rule out volcanism either. Then also the question is, all of that alteration that we're seeing, the water-rich parts of the meteorite, when was that implanted in the meteorite? When did that get put into the meteorite? When was that early, 4.4, or was that during this mid-Amazonian event, 1.5? That's one of these things that we're still trying to work out. But so this is just an overview of Martian meteorite ages. Classically, we've had the Shergottites and the Knocklites and the Chassignites all being recognized as relatively young volcanic rocks. Well, the Shergottites certainly in the last 600 million years, their formation ages. Knocklites and Chassignites are around 1.3. Allen Hills is a fairly old rock. That's Singleton, orthoperoxenite. Larry Nyquist's age is out here, and this is a more recent age from University of Houston. This is that augite basalt that I was talking about. That's that new one that we're still working on. And these are the ages then from Black Beauty. There's an ancient age from Samarium neodymium from Nyquist, and also the old zircons. And then there is the young zircons and young bedelliites, and then there's that rubidium strontium age of Asmarov that sits there. So Black Beauty is recording within it not only this geologic field area from which all these clasts come, but it also is sampling geologic time on Mars. And there are events that are hidden away in that meteorite that we're revealing with this age dating. There may be more. You know, I'm still curious about this rubidium strontium age, but clearly the uranium lead data shows that there are these two ages, young and old, that are present. Just a note about the water. We extracted water out of NW 7034 at UNM. This is work that Karen Ziegler did primarily, and we found these are just two plots of two different runs on chip from the meteorite, so bulk sample. And we have over on this side delta D, and here we have percent water evolved, and it's done stepwise. It's stepwise heating, and so you can see that in both experiments we had a big release of water, the blue, at somewhere around 200 to 400 degrees, where most of the water came out. A little bit of water came out at low temperatures, and a little bit of water came out at very high temperatures. And you can see in terms of delta D that we have negative values, and then they ramp up as we go through this big water release and get up into the plus 100s. So what we're sampling here, of course, is the release of water out of those mineralogic phases that I was describing earlier. And again, the question is, were these implanted? Was this water incorporated into the meteorite in the Amazonian, or is it early Noachian? And so we went in to look at the water, the phases that bear the water in the matrix. So we used TEM work primarily and SEM work to delve into this, to get down to the finest scale that we could find in this meteorite. You know, so the meteorite is fragmental at the coarsest scale. You know, and probably if you saw Boulder this year, maybe there are big fragments within it. But then as you go down into it, it gets to the micron scale, and it's still fragmental. And then you get down to the submicron level, and you finally find things that look like a mosaic that are not fragmental anymore. And so this is this very fine-grained, finest scale of the mineralogy of the meteorite, and it looks like it's been sintered. Just those finest grains, because they form triple junctions. But in any case, in here we can see chlorine apatite, maghemite. There are phyllosilicates that have been identified with the TEM, and ferrihydrite. And this is just a slide that is trying to explain how we come to this this value of 6,000 parts per million water for NWA 7034, because it's a huge amount of water compared to other Martian meteorites. Martian meteorites Normally, like Shergottites, the basalts have something like on the order of 200 to 300 ppm. So this is, 10 to 30 times higher than the garden variety Martian meteorite. And so we're just saying, well, you could get 1,000 ppm out of ferrihydrite. You could get maybe 1,000 ppm out of this 5% maghemite that's present. Say you have 1% phyllosilicate in the rock, you get maybe 1,900 ppm. And then the chlorine-rich apatite, which is abundant. Oops, something happened. What do? Okay. It doesn't have a lot of water in it, but there's so much of it around it could give up to 150 ppm. So again, where did the water come from? Well, we know, of course, that the Martian soil is full of water. We know that from Odyssey Orbiter. And so, for example, if we had you have an impact on Mars, you can actually, presumably, you can set up some sort of hydrothermal system. Give it a heat pulse and free up that water and start circulating it through the rock. So that could be a possibility. The other, of course, is that it could be volcano-induced. It could be volcanism, and there's no reason why that can't happen. There are both things on Mars: impact craters and volcanoes. So take your pick. And so whether or not the early Amazonian looked like this, I kind of doubt it, but you never know. We know that Mars looks like this today, but there's still abundant water to be incorporated. It just needs the heat energy to make that happen. Is there a question in there?
Did you measure the soil in Sahara for the delta T? Because minus 100 mil is pretty light compared to current day Mars.
Yeah, I think it would be a general really good idea to characterize the Sahara better in terms of weathering. But we haven't gone and done that, right? But the low values that we see at low temperature, we were interpreting those as being terrestrial, contamination. But turns out in Mark Beeman's lab, they did oxygen isotopes of the water, and that first 50-degree water that comes off does not have a terrestrial oxygen isotope value. It has a Martian one. So Zach is then saying, well, these Mars may have two water reservoirs, a negative one and a positive one. So, the jury's still out on that. Yeah. So we know that there's no surface water in the late Amazonia, or at least we're there right now because we have rovers on the surface, and the water is locked away. But of course, 4.4 billion years ago, when those zircons were formed, and presumably the igneous clasts that contain them, and most of that meteorite, maybe Mars was a blue planet, and maybe the surface water. This, by the way, is not Earth. This is, you may recognize Valles Marineris here, full of water, right? And these are the northern highlands, except they're now an ocean. Maybe that's when the water got incorporated in Black Beauty. So.
Is that vegetation?
Yeah, it is actually. There are mammoths here, roaming. They're grazing on the vegetation. If you look really close, you can see it. And so now I want to finish off with showing you some tomography we did on Black Beauty. If I can get that to work. Yeah, there we go. So what we decided to do, you saw how I started to go at that meteorite, with my rock saw, and the trouble with the breccia is that you cut one time and you say, okay, that's fine. And you go, I wonder what's the next slice is going to show, right? And so you keep cutting on it. And like the guy who owns that sample. I mean, we got some of it as a deposit sample for the museum. The main mass belongs to a collector, right? So he's going like, how much did you cut off of that meteorite? And I go, I don't know. Let me weigh it, And so like, there's 270 grams left, So he said, what? Stop cutting it. But so what you can do, instead of completely destroying your meteorite right off the bat, you can do tomography on it, right? And so you can say, oh, let's see what's on the inside without cutting it open. And so that's why we did some tomography on some pieces that hadn't been cut open. And so what you're seeing here is sort of a targeted tomography. It's on a segment of a piece of black beauty. So this is not actually cut off, it's just cut off in the picture. And we just focused on this one part because it had an interesting feature hidden away in it. This is X-ray tomography done at 2.2 micron voxel resolution. It was done by Doug Rowland at UC Davis. And so let me turn this thing on. Hey, there it goes. So it's should be color coded to show, yeah. So the high Z domains are showing up as yellow and green, and the low Z are showing up as the blue. So the domains that you see in there that are light are things like iron oxides and titanium rich phases. And the intermediate iron are the blue, and then the transparent part is the low Z material. And you can see in this particular tomography setup that we managed to target one of those spherules. And this particular spherule is actually more rich in feldspathic and pyroxene components than it is in magnetite. Then we took a bigger piece. This is that, remember that piece that was sitting in the desert? The 241 gram piece? We did that one also. And it's at 42 micron voxels because it just ends up being so much machine time that it gets to be very expensive to do this at higher resolution. But it doesn't really matter what resolution you do, you're always seeing something that highlights where there might be a sphere or some domain that's of interest. And in addition to X-ray tomography on this particular one, we also did neutron tomography. So this particular slide shows first X-ray, and then it shows neutron absorptions in a different color scheme. So this is the same color scheme as we saw before. So transparent is very low Z, blue is intermediate, and the yellow and green is high Z. And the idea of going to neutrons was to highlight possibly the presence of hydrogen. Hydrogen has a very high absorption in neutrons, and so this is again still the X-ray. And so so we were thinking this might be a good method to use to be able to target domains within the meteorite that are water rich versus those that are water poor, water depleted. So here's the neutron scan. This is coming up now. So the reds, I mean, if it's true what I said, then the reds could be perhaps more hydrogen rich, and the blues would be, for example, hydrogen poor in this meteorite. We haven't verified that, but it was the reason why we decided to go ahead and try this to see if we could what the meteorite would show.
What's the energy of the neutrons you use?
You know, I'm not sure right offhand. Yeah. Okay, that's all I had to say.
Any questions, Carl? So what's the next steps? I mean, it looks like there was still lots of interesting stuff there, and
yeah.
And how is people just come requesting sample from you, or how is the process?
Yeah, I mean, originally I allocated a lot of sample, and we went through a lot of material. So, but we still have we have specimens for non-destructive use that we're happy to lend. The destructive, when somebody tells me they want to have some sample that they won't be able to return because of destructive analysis, I refer them to a collector so they can buy it, because it's too scarce, and so that's how we do that. So we do allocate it, but there are many ongoing studies right now, just like the one that McCubbin is doing now. So
Yeah, have you been able to date any of the specific class, you know, on your TAS diagram to put ages on the spectrum of class you have in there?
Only in the sense that an included zircon was in one of the micro basalts or micro gabbros.
Sure.
So remember those pieces that had the beautiful mosaics of pyroxene and plagioclase. Some of those had datable zircons in them.
Okay.
So those were done with either the shrimp or with the nanosims, and so if you believe that is an age of the class, yes, and those are 4.4. So far the one or two igneous class that have actually had datable zircons have yet come up with old ages.
So most of the sort of matrix source zircons are younger.
It's a
younger
mix.
ages.
It's a mix. Yeah. Yeah.
So presumably the water measurements were made on some subsample of the rock. So how do you extrapolate the 6,000 ppm for such a heterogeneous?
It's first cut, right?
So it's 6,000 ppm in the stuff you analyzed.
In the bulk. In the bulk. Yeah.
But was it a representative bulk sample? I mean.
Of the pieces that we had. You know, this is always the problem with breccias, is that, you know, someone sends me a breccia, and it's always tough because they'll say, oh, well, didn't you see that, you know, that dark class? And I said, no, I didn't see that. It wasn't in the piece that you sent me. So there's always a possibility that you're missing something in a breccia, so it's obvious to do more work. But we consumed a lot of material. We consumed, you know, several grams of material. And, you know, this meteorite went from, just as an aside, that original piece was purchased out of Morocco for $5,000, you know, that 320 gram piece. And right now, the meteorite's assessed at 6,000 a gram. So when you start using up lots of grams, it gets to be expensive. But yeah, we did it. And so you know, there's more work to be done on that part of it.
So going back to your zircon dates,
Yeah.
I think you said that the younger dates are associated with an impact event.
Well, it could be. I mean, it could be an impact. It's not the impact that launched it.
Sure.
It's assumed, well, that because there is this mildly annealed, very fine-grained matrix, that we are interpreting that to be the result of a heat pulse at some point later, probably when the thing was made into a breccia. And so the idea is that the young ages could represent that. But we don't really know what the young ages mean, you know. It's always hard to decide what that means because it may not be a crystallization age, you know.
Well, I mean, I wanted to follow up on that because two things. It seems to me there could be plenty of Martian surface rocks that are 1.4 billion years old, and if you have a breccia, how do you know you're not sampling them? And normally, if you have an impact, you would expect that heating materials sufficiently, you would expect to see evidence of shock too.
Yeah.
Do you see that in the zone?
No,
Do you think we reset?
No, the shock in this this is the really interesting thing about this meteorite, even though it's a breccia. And this is what made me think it was volcanic originally, is that there's no mescalinite in it. You see all this plagioclase. For those of you who are not familiar with this in Martian meteorites, the basalts, they're full of feldspathic phases, but it's plagioclases that has been shocked into an amorphous phase called mescalinite. It's like a glass. Black Beauty has none of that. All of the feldspar in there, whether it's plagioclase or alkali feldspar, it's all crystalline. It has no shock melt veins in it. It does have some clasts in it that are that look like they're rapidly quenched, but they're fragments of something. They could be from a chill margin, but they could also be from a shock. You don't know. So even though the thing is very, broken up, it's not like the classic sort of shocked meteorite that's got tons of shock melt and all this mescalinite. So that's.
I'd be surprised if you could reset a zircon without using mescalinite. But
Yeah, no, the zircon, I haven't done this work myself, but I know that we had a collaborator, or someone who was working independently of us I've forgotten now the fellow's name, but he's at Western University, and he did in Canada, and they did an analysis of the zircons. They found one zircon that looked like it had been shocked, and all the zircons that they looked at. So the zircons look good. Yeah.
Zishue and Bob.
I just wonder for the zircon, do you have any inclusions that include the zircon, so that might tell you something about
Some inclusions in the zircons.
Yeah.
I'm sure there are some that have inclusions in them. I personally haven't worked on the zircons. Francis McCubbin has worked on the zircons. Nemchin has worked on the zircons. Again, there are a few groups that are working on these right now. So that's not my area of expertise. So I can't really talk about it specifically. But I know that their main interest was finding large enough zircons to do the microanalysis on them. So there are plenty of those.
Bob?
So people must have done statistical studies on size distributions and lithological variations on lunar breccias because they're so abundant relative. Is there any comparison you can make between Black Beauty and what's been found with the lunar breccias?
We haven't gone in and done a study on that by any means. I mean, all I can say is what I know from having looked at Highlands rocks myself, and these are quite different. You know, the typical feldspathic breccia is full of shock melt. Sometimes the feldspar is mescalinite, not always. The fragmental part is very similar, but there's not this pervasive shock melt that you see in lunar rocks. But I would say that probably it's the closest thing, would be the lunar Highlands rocks to this sample. But again, it's again because of the water there and the sedimentary features, it's still its own thing. It's really quite. So I keep going back and saying, well, this is typical of Mars and not typical of anything else.
Any other questions? And
so for isotopes, you showed isotope reservoir, which is more heavy in oxygen. So is it fair to say it's mixing with reservoir close to
We don't know for sure what it is. I mean, it could be, but it could also be that that Mars is heterogeneous with respect to oxygen isotopes, and that the Shergottites, the SNCs, are actually sampling their own reservoir, and that we don't have oxygen isotopes from NASA rovers or orbiters or anything, obviously. So those measurements have never been done. And so what would be really interesting is if we could ever get some Mars samples back from missions to verify whether or not Mars has multiple reservoirs of oxygen. We have evidence that it is.
Martian Meteorites and other breccias?
No.
No one ever
This is the only polymeric breccia.
And did you measure stable isotopes of
Have not. We've done, Xingzhu Yin has done chromium isotopes on it.
We measured the iron and they were 100.
Oh, did you? Okay. I don't know what everybody's done, actually. It's proliferated, to the extent that there are lots of studies going on that I'm not up on completely, but yeah.
Are there noble gas data besides argon isotopes? And do they also look Martian?
Yeah, there's, I'd have to go back and, I just showed you argon, but
Right.
they did, I'm just trying to think of what exactly she did. I'll have to refer you to the paper.
Okay, it was EPSL Cartwright?
Yeah, that's right, yeah. I just picked out the best diagram for the talk. Yeah.
okay, if there's no other questions, let's thank Carl again. Carl will be here and all day, and there is a window. It's kind of open discussions. It's particular for the young scientists and postdocs, not on the schedule, and we have a block of the time between 4:30 to 5. I think meet at the board.
Yeah. Yeah. Absolutely. Yeah. Yeah. Do you want to have the PowerPoint? I can put it on Dropbox and you can just take it. Yeah, absolutely.
Oh,
Yeah.
okay. I'm just trying
It's on the computer. Yeah, take it off the field. Be my guest. Yeah, I have more movies.